Hello and welcome back to ICFP 2020. And our next paper is going to be computational focusing, and it's going to be presented by Nick Ryu.
My name is Nick Ryu, and this talk is for the paper called Computation Focusing by myself and my advisor Steve Zdansiewicz at the University of Pennsylvania. Our paper is all about proving program equivalence. This is an important way of reasoning about them. So whether you have a compiler that performs CPS translations or just some optimizer that does function inlining, in order to justify them, you're probably going to want to be able to prove programs equivalent. The sort of gold standard of equivalence, the notion that we care most about, is called contextual equivalence. And two programs are contextually equivalent when they show the same behavior in all contexts. There's no way to distinguish between them. But proving this is difficult because there's so many different possible contexts that programs could be used in that we can't really just do a case analysis on all of them. So we need other techniques to prove equivalences, and the CIU theorem does this. It allows us to, rather than consider all possible general contexts, only look at evaluation contexts paired with closing substitutions. But there's still difficulties here, and in particular in call by value, there's still many possible evaluation contexts, so it's difficult to reason about the interaction between a term and its context. And call by name has a very similar dual problem. So another class of syntactic proof techniques includes logical relations and bisimulations. Logical relations in particular give you really nice high-level reasoning principles like relational parametricity. But there are still some limitations, and one of those limitations is that some equivalences between existential types have not been easy to prove in the past using logical relations. And the problem is essentially that logical relations are just more naturally used to reason about how a program produces an output than how it uses its input. So let's look at a particular value of this existential type. And let's look at how these values of this type are used. Well, we used existential types by pattern matching on them to unpack them, and here we unpack this existential into a function y. And this y is a higher order function, so we pass another function f as input into it. And f has the type x arrow x, but this x type is an abstract type, and so f must be the identity function. So with that in mind, let's look at these two values of the same existential type. They contain functions that themselves take another function as input, f. And they both apply f to many different values, checking to see that it does indeed behave as the identity function. Since we've already shown that this is true, we can look at the functions in these packages and confirm that they both are always going to return true no matter what. So in other words, this means that they must be equivalent. But logical relations and bisimulations struggle to prove this because they force you to come up with some relational interpretation for x that somehow relates values of Boolean type to values of integer type. But we have no such relation in mind here. There's not really a correspondence between values of x in one of these packages with values of x in the other package. So instead what we want to do is look at the possible context these values may be used in and exploit the fact that they're constrained by their types. So throughout the rest of the talk, we're going to look at a proof theoretic technique called focusing and show that that's actually useful for reasoning about programs. In fact, we can use that to prove this equivalence. Lastly, we'll see why this technique might be useful in compositional compiler correctness. For this talk, we're going to deal with a call-by-value language with predicative polymorphism in a pure setting, but the paper goes beyond some of these restrictions. So what is focusing? Well, focusing is a proof search technique that narrows down the search space when you're trying to find a proof of a certain proposition. And viewed through the lens of Curry-Howard, you can think of it as making things easier when we're trying to synthesize a program of a given type. So how does focusing narrow down the search space? Well, it does that by visiting fewer redundant terms that are just equivalent to each other via beta or eta laws. We don't have time to go into focusing in depth today, but I want to give you a flavor of what the focused terms look like. So let's try and visit all the focused programs of the Boolean to Boolean type. The first thing that focusing says we can do is apply the lambda type constructor anytime we have a function on the right-hand side. It says that just any term in our language of function type is going to be equivalent to some lambda. And that's true by eta in call by name, and in call by value we're also using normalization. But if you didn't have normalization, you could still use this technique. You would just have an extra non-terminating term to consider. So now we need to consider what the body of the lambda might be. And when we're trying to build that, focusing says that the first thing we can do is eagerly pattern match. Anytime there's something in the context that can be pattern matched on, focusing says we might as well do that pattern matching right now. There's no point in waiting until later. So now we know that all the terms we're interested in have a lambda on the outside and then immediately pattern match on its input. And what we're left to build are the two branches of the if statement. Both of these are closed because focusing knows that there's no point in pattern matching on x twice once we've already done it. And so we just need to build focused programs of Boolean type. And it turns out there are only two of those, true and false. And so we can use those to build our 4 candidate programs here. And it turns out that every function of Boolean to Boolean type needs to be equivalent to one of these 4 focused programs. We've cut out many, many non-focused programs, such as the identity function lambda x.x, but this program is still represented in the second bullet point here. So some properties of focused terms that to keep in mind are that focused terms are always beta eta normal. There's no way to beta reduce them, and they can't be eta expanded without introducing a regex. And we characterize them in our paper as a restricted type system. Basically, the usual type rules that you're used to, but restricted to be applied in a certain order. And this gives you strong inversion principles to do programmatic reasoning. Lastly, for every focused term, for every well-typed term, there's some equivalent focused term. This is called computational completeness, and it's the key property we need for reasoning about programs. And basically all it says is that we may have eliminated many redundant representations of the same program, but we haven't lost anything of value. There's still some representative focus program for any other program. So why are we talking about a proof search technique in a talk about contextual equivalence? Well, it turns out that a proof of contextual equivalence is just a search through all possible contexts, demonstrating the same behavior for each context. And so if you think about it like this and you apply the completeness of focusing, then you can see that there's no need to search through all possible contexts. You only need to search through focused contexts. So that leads us to a context lemma, which looks a little hairy, but all this is saying is that to prove two values equivalent, you only need to consider focused contexts, which are represented by a term nf with a whole x represented as a variable here. And if v1 and v2 are open, then you need to close them off with some closing substitutions, but you can assume that all the values in those substitutions are focused. So let's return to the equivalence that we wanted to prove earlier, and now we'll apply our focusing lemma. And this context lemma says, since these values are closed, we just need to consider some context nf and show that they both behave the same when the values are filled in for x. So what does the fact that nf is focused tell us? Well, the whole in nf x has existential type, and we know that existential types can be pattern matched on. So focusing says, let's do that right away. Now once we unpack the existential, we get this function y, and the rest of the body of the pattern matching statement gets to call y potentially. So there's really only two things that we can do here. Either we call y or we don't. And if we don't, then we can only return a constant Boolean value. So there are 3 possible shapes of programs here that this context may take. We need to show that the two values behave the same in each of them. This is easy in the case of the constant Boolean because the context just ignores its input. The interesting case is when we call y. And what happens here is that v1 is going to get destructed and substituted in for y. And it's going to get passed in f, which we've talked about before must be the identity function. So if you plug the identity function into the functions in v1 and v2 and you reduce, you can see that both of them return true. So what's left in the proof is to show that z is equal to true in both cases. And that, combined with a small detail about the proof structure that you can see in the paper, let us complete this proof. Now that we've seen program equivalence, let's look at compiler correctness. One property you might want about your compiler is that it preserves all of the abstractions in the source language. So to say this more precisely, you can say that two terms in the source language are equivalent implies that after you compile them, they should still be equivalent. To prove this, you need to consider an arbitrary source target language context, C prime, but we have a source language equivalence to use, so we need to back translate the target context C prime to a source language equivalence. And the key idea that focusing helps us with here is that we don't need to back translate every single possible target context, we only need to back translate the focused ones. There's a long history of using focusing in proof theory, but there's also related work here that uses focusing in the context of programming languages, especially as a guide to design features of programming languages. There's also work that uses focusing as a normalization procedure to decide the equivalence of terms in the simply typed lambda calculus. Lastly, normalization by evaluation is pretty relevant because it could be used to prove our completeness of focusing theorem. There are many different type system features and effects that we might study, and we expect focusing to be a useful tool along with all of these. In particular, the combination of linearity and focusing is really interesting to study because that's where focusing originated, and because linear lambda calculus terms have very nice normal forms that make them easy to reason about. To recap, our paper contributes a few things. First, we formulate focusing in a call-by-value language with predicative polymorphism, and we provide a proof of the computational completeness theorem. Then we prove a context lemma and show that that's useful in turn to prove various program equivalences like the one we saw today. Finally, we show that focusing can be used to prove compositional compiler correctness properties like full abstraction. And we do this for a simple compiler from a language that's pure into a language with a simple divergence effect that's tracked by an effect system. That's all for focusing for now. Thank you.
Right, so thank you, Nick. If you're interested in joining the authors of this paper for a live Q&A and you're in the New York time zone, then you can click on the link in the Clouder room.